So finally, we've been able to reach the end of chapter 8. There's been a lot of stuff in it, big long chapter. So let's make sure we finish up strong here. A few points to keep in mind before we get going with an application of cross products. So they're not brackets when you do these. Okay, we're not doing matrices with them, but they're kind of up and down lines, not absolute value things, but discriminants. Okay, so when you're writing these, don't curve them in and create brackets. They're just up and down lines for your discriminants. So when we say discriminant, it's the idea of cross multiplying and subtracting, okay, for each individual discriminant. So our formula that we practiced yesterday is plus the discriminant of this guy minus the middle discriminant plus the last discriminant. And each of these needs to be cross multiplied and subtracted. If we want to find the vector orthogonal, which means perpendicular to two different vectors, so you got any two vectors in space, let's put one right there, let's put another one right here. If we want something exactly perpendicular to it, so coming right out at us from the computer screen, all we do is find the cross product. Okay? By definition, that's what it does. And when you're doing dot product, you get a number, not a vector. So take out the i's, j's, and k's. Okay? So we left off yesterday with some geometric properties. We're going to finish the rest of those guys up. Here they are. So geometric properties of the cross product. So if you got any vector u and any vector v, and it's in space, so 3 dimensions, it's in the room, wherever. So if you do the cross product, it's orthogonal to u and v, okay, by definition. So anytime I give you two vectors and I say find something orthogonal to it or prove this vector is orthogonal, you need to find the cross product. Now this one's kind of interesting here. If you do the magnitude of the cross product, it's the same thing as doing magnitude of u, magnitude of v times sine of theta, where theta is the angle in between u and v. So we've done formulas where we've used theta, but it's always been cosine. And that's let us find the angle in between it. Okay? Now the proof for this guy is pretty neat, and I'm going to show it to you guys from the solution book just so you know where this guy comes from. So we have to assume this thing right here. Problem 57 proved that these are true. So if you do the magnitude of the cross product squared, it's the same thing as magnitude of u squared, magnitude of v squared, minus the dot product squared. Okay, so we're just going to assume that that's true. It is. You can see the big proof up here. Certainly that's a lot of work. Now, they're going to do a substitution here for dot product. Okay, so we know that if you want to find the cosine of an angle, it's the dot product divided by the magnitude. So if we solve that equation for the dot product, we substitute it in, we get the magnitudes times the cosine. So this formula here, simply all we did was if we want to solve for the dot product, this gets multiplied to the other side. So they put that substitution in right here. Okay, they're going to apply the squared to everything. So magnitude of u squared, magnitude of v squared, cosine squared. Now this is kind of interesting. They see these are the same, so they factor it out. Just like if you had, you know, with numbers here, like 2 minus 2x squared, you'd factor a 2 out. So they did that here. You're left with a 1 minus a cosine squared. Identity from a long time ago, that's a sine squared. So therefore, if you square root both sides now, magnitude of the cross product is u, magnitude of u, magnitude of v times sine of theta. Okay, so it's a neat little application to see that. So we prove this one here. Now, magnitude of u cross v is the area of a parallelogram. Okay, so if we take 4 points in space or any two adjacent sides, we can create a parallelogram with them. If we want to find the area of that thing in space, okay, we're going to do the cross product, and then we're going to do the magnitude of it. Okay, and lastly, u cross v equals 0 if and only if u and v are parallel, that kind of makes sense. By definition, a cross product is something perpendicular. So if you got two vectors that are parallel here, it's pretty tough to make something perpendicular to it because really you only have 2 dimensions now. Whereas if I had two vectors like this, I can do something perpendicular coming out right at us. But if they're parallel, it's tough to make something perpendicular to it in space. Okay. Here's kind of a picture illustrating why some of those things work. So we know area of a parallelogram is nothing more than base times height. Well, if it's in space, it becomes a little bit more difficult. So let's say we get this parallelogram here formed by vector v and w in this case. So here's that theta. It's going to be the angle in between them. Well, we know from geometry that heights of parallelograms always have to be at a 90-degree angle. So we're going to take this little triangle here, and we're just going to do a simple little sine ratio. So opposite over hypotenuse, where this guy is vector w. So if you want an expression for the height, we would simply solve for that, and we would get magnitude of w times sine theta. So if you want the area of this parallelogram, magnitude of v, magnitude of w times sine of theta. Okay, which is this guy right here. So this also lets us find area of a parallelogram. Okay, we can do it 2 different ways. Now let's say you're not able to do the cross product. You could do magnitude of u, magnitude of v, and sine of theta. So both these will work for area of a parallelogram. Okay, another picture here. So here's, a figure in space. It's got many different parallelograms on it. If we wanted to find, for instance, the area of this front face here, here's our base. Our height would come down right here. Okay, so we'd use that sine ratio there. And obviously you could find area of any one of these 8 faces on here. Okay, or 6 faces, I guess, for a prism in space. All right, so area of parallelogram, magnitude of u, magnitude of v times sine of theta. Now, I'm going to give you guys this problem here. So find area of a parallelogram, here are the adjacent sides. Now your book gives you an example, I'll show you in just a minute, where it doesn't give you the adjacent side, it just gives you 4 points. So it makes you find the vectors with the adjacent side. Okay, so basically position vectors for them. Now, if we know these are the adjacent sides, so they're going to form, something like this, something like this, it's going to create a parallelogram. So we can assume, it comes out like this and something like that to make a full parallelogram. But we're only given those vectors that are solid there. Okay, that's enough to find the area of that. Again, we need this little guy right here. So I'm going to do both formulas here for you, and you guys got to decide which one works best for you. So let's look at this guy first. I'm going to call this vector u. I'm going to call this guy vector v. Right, so I need to find magnitude of u. So that's 9 plus 4 plus 1. I need to square root that, so it's square root of 14. So I think we've seen that one before. I need to do magnitude of v, so 1 plus 9 plus 1. So that's square root of 11. So I've got this and I've got this. Now, sine of theta. Okay, I don't know what theta is, so I'm going to go back to our old formula here and find it. We know cosine is the dot product over the magnitudes. I already got the magnitudes. I just simply need to do a dot product now. So this is negative 3 minus 6 minus 1 all over my magnitudes. So that gets me to negative 10 over square root of 14 square root of 11.